Let's look at time derivative of moving vectors. Okay. You have the I. This is all caps, okay? Begin K. You can say this is the y direction, x direction, g. And you have a moving frame. Small I. Small j. And small k. Let's say you have a vector b. So this is often the case. When is this the case?
You say like something is moving,
Yeah, you can think about this as
like an airplane.
airplane or a spacecraft, and this could be your position vector, okay, some vector, where you are moving within this body or within this frame, and this frame itself is moving with respect to some fixed frame. Let's call it the inertial frame. So you have to look at this invites discussion for inertial and non-inertial frames. Okay. I may ask you a question in exam, what is an inertial frame? Explain with an example what is a non-inertial frame. Or I may give you an example and state whether that's an inertial or non-inertial frame. Okay. So what's an inertial frame?
Something moving in respect to something fixed.
Inertial frame is something which is either fixed or moving at constant velocity. A non-accelerating frame. Does that make sense?
Something can be fixed or not accelerating.
Non-accelerating. Something which is non-accelerating means it is moving at, it has to be either, yes, it has to be moving at constant speed or it has to be fixed, right? Non-accelerating. If it's accelerating means, is the velocity the same?
No.
It's going to change, right? So an inertial frame by definition is a fixed or a non-accelerating frame, okay? Or a frame moving with constant velocity, okay? So what when you apply Newton's laws, they have to be applied in a inertial frame. So if you apply Newton's laws in something which is accelerating, like for example, plane or aircraft, you won't get the proper result. You cannot experimentally validate the motion in a non-inertial frame. Got it? So if you want to, yes.
You said constantly is accelerating.
Non-accelerating.
Okay. Okay, so, like,
Constant velocity.
the plane will be the one on the top right.
This is a non-inertial frame. This is a moving frame. Okay. Strictly speaking, there isn't any inertial frame in the universe.
That's what I was gonna ask you. Like, the Earth is always moving.
Right. Earth is always accelerating, right? Is Earth accelerating?
No, it's not. Is the Earth accelerating? Then it moves at constant speed.
No, it ain't separate.
It's speed up. What's up?
Yeah, for certain points, right?
The Earth speeds up and slows down at a certain point in time. I'm asking, not saying.
So if you're in a circular orbit, there are
I'm not saying that the Earth is already has the Earth has constant velocity. There's the velocity change.
there are two velocities. So if you have to look at, calm down. You have to look at, of course it is moving tangentially, but there is a radial component which is pulling it down, right? It has to accelerate to keep moving it away from that. Otherwise what happens?
Yes,
It will spiral in, right? If there is a radial acceleration which is pulling the Earth is being pulled towards Sun. It has to keep on going away from that, right? So that is where acceleration comes.
Okay.
If you're looking at, so Earth's orbit is, we'll talk about this. Earth's orbit is an elliptical orbit. Elliptical orbit means it's not moving at a constant speed. It has to accelerate at points and it has to decelerate at points. Okay, we'll talk about that. So, inertial frame, there isn't any practical example for inertial frames. Okay, but what Newton did was he said, assume there are a set of points which are moving at constant speed. All right, and he said the laws will apply in that frame. Okay. Now, for practical purposes, what you can do is you can attach something to Earth, okay, which is not rotating along with Earth. Does that make sense? It's only moving around the sun. Earth is doing this, plus it is doing this, right? So you attach a frame which is not doing this. Does that make sense? Yeah. Earth is doing this, and it is doing this. This is pretty high. Even this is acceleration. Okay. So if you attach a frame,
I see what you're saying.
yeah. So if you attach a frame which is not doing this, it stays like this, but it slowly moves around the sun. That would be a inertial frame. Okay. So you have that frame. That is a practical inertial frame. It doesn't have. It is almost a non-accelerating frame. If you have this frame, which is also rotating along with Earth, that is a accelerating frame. That is a non-inertial frame. Okay. Yes.
So just a question. So if the moon was not rotating around the Earth, but it was going around the sun with the Earth, that would be the inertial frame.
That would be the inertial frame.
Okay.
Okay. So, but moon is also doing that, right? So, what happens is you have to look at, there isn't anything that is fixed. Everything has some angular motion. Unless there is control, external control executed on that, everything is doing this. Right? All planets are doing it. Now, what I want you to understand here is you can express V as Vxi plus Vyj plus Vvk. Okay. What is this vector can be coordinatized in this frame or this frame. Correct? What is that? That is coordinatized in the inertial frame. Okay? But typically what happens is you cannot really know that, right? How you are moving inside a spacecraft, inside an aircraft, with respect to a fixed is very difficult to figure out. Right? So if you have dv by dt, you're going to get bx dot I plus by dot j plus bz dot k. I dot j dot k dot is 0. We discussed that yesterday, right? Because the frame is fixed. Okay. Now think about this is an inertial frame. Both these. Okay. Now think about D as so I'm going to make this like this. Okay. X. Just capitalize it. This I'm going to call as Z. So you have x, small I, okay, plus k. Now B would be what? Plus does this make sense? Here, this is in what frame? This is in moving frame, yes. Okay. So this is in moving frame. You can see that if I took the derivative here, it will be bx dot I plus bx I dot. You see those two terms here? This I dot is this, I is this, and I dot, this is moving, right? So it is changing. You have those three components as well. Does that make sense?
So when it's changing,
It is moving means there is a derivative. With respect to time, there is a derivative. If it is not moving, the time derivative of this would be 0. The frame. You understand? Okay. Now what we typically do is, let's say the angular velocity is omega, angular velocity of this frame. Okay. So you represent di by dt, which is I dot by omega crossed with r. Similarly, j dot is omega crossed with j. dot is equal to omega cross. Okay. You can write this so B dot can now be written as dV by dt relative plus omega cross with B. Okay, just be with me here. And what I use this notation quite a bit. Okay? B is circle dot plus omega cross with.
So what does this mean?
What's circle that?
Yeah, I'll talk about it. So, what you're trying to do here is this component is this component. Got it? This component is this component. This component is this component. Okay?
You usually use different color markers.
Sure. This component is
The G star. So is the omega and the B supposed to be on the one?
this component.
What about right there in the middle?
This
Yeah.
is actually this component.
The way that's looking.
Right. So this is, so I've used this, right?
Yeah.
Now, if I substitute, I'm going to erase this.
I take pictures of that real quick.
I'll just use that part, it's visible. I'll try to use it within. I think it's visible up to this point. Okay. If I substitute these, right, in here, what I'm going to get is, I'm going to get B, so you have B dot is equal to, I'm just going to write this as this, okay, dB over dt relative plus it will be dx omega cross with I plus dy omega cross with G plus dz omega cross with G. You with me, Marcus? This clear? I've just substituted for I, G, K. I dot, J dot, K dot. Okay? So, this
Excuse me, talk for a second.
yes,
I need to get onto that computer. I need to get onto that computer for a second.
can you just wait for a few?
Well, kind of, yeah, at 10 there's a meeting.
This is can be written as omega crossed with d. Does that make sense? These three can be written as this.
Okay, just sound like
I combine all of them and write it like this.
So if we were doing this like on the test,
Huh?
if we were doing this like on the test, we would just skip to straight to it.
Yeah, I won't ask you to derive this.
Okay, so
Okay, I want you to understand. I'm going through this to, at some point, you need to derive this, not as part of this program. But if you go outside, you should know how to derive this.
so which part do we need?
The B open circle plus omega.
Okay. So what it says is, now pay attention here. Stop writing. Okay. I am taking the derivative. This and this is the same.
Yeah,
Okay.
the inertial.
Inertial. If you are doing the inertial frame, right? So here, this b dot and this is the same. This is the derivative of this vector in this frame. You understand?
So B circle dot is.
B circle dot is the local derivative. It is how you are moving inside an aircraft. Does that make sense? This B dot, circle dot, is how you are moving inside a spacecraft or inside an aircraft. Guys, pay attention here. Does that make sense?
Say it again. Say it one more time.
This is the total derivative of this vector. Okay? The total derivative is equal to its local derivative, how it's moving in this frame, plus how this is moving with respect to this is this. Does that make sense? This is the total derivative. Okay? This is the local derivative, and that how you are moving inside a spacecraft or an aircraft.
Gotcha.
This component, second component is how the spacecraft or the aircraft itself is moving with respect to the inertial.
I got a question. So how do you get the unit vector I of dt equals that equals American times I unit vector? How do you get that?
This one,
Yes, how do you get that?
that is how you can express it. Don't worry about how to get it. It is another way of expressing it. Okay, I dot, that is how it is moving. So here what is happening is this is doing that. The aircraft or the spacecraft is having angular motion, and what you're doing is you're expressing that as cross of these two. That is just another way of expressing it. Okay, but I want you to understand this. Okay, these two are the same. What is this part? This is the circle dot. Got it? Circle dot means it's a local derivative. Have we applied Newton's laws here? We have not applied Newton's laws actually. We have just done kinematics. Kinematics does not involve Newton's laws.
So is that B dot the same as that?
Right. This B dot is the same as this. Okay. This component is this.
So
This component is this.
Can you say what the omega cross B is again?
Hmm?
Can you say what the
Omega cross B is this.
No, like how you were saying that's total. Omega
Right. So omega cross B is how this frame is moving with respect to this frame. Does that make sense? If this frame is not taken into consideration, it's this. If you just ignore this frame, this is the complete derivative. Okay? But this is not practical. You have to understand that.
So
Can you figure out your position inside a plane with respect to is the air traffic control going to track each individual, how they are moving?
No.
Or is it easier to track how the aircraft is moving and somebody is trying to track your motion inside the aircraft? That's more practical, right? You understand? Yes.
My only question is, I thought you told us you can't, well, never mind. So you're going to be taking a cross product of two vectors and then you're going to add another vector to it, right? At the bottom, where you told her, is that what's happening?
Mm-hmm. Any questions?
So
We're going to use this quite often.
So we don't really know how you got the B, DI over DT equal.
Yeah, I won't ask you how you got this. I just need you to be able to use this in a when it is relevant. For example, I may ask you to derive this as part of your homework, which you should be able to spend time and do this, but not for an exam. An exam will be too lengthy. I'll give you an example, for example, and ask you to apply this for your homework. That is okay, right? But I won't ask you to do this in a
Test.
test. But you need to know how to apply this in a test. Does that make sense?
Is
This and this are the same. Okay?
is V up in circle, is that like a position or is that movement?
It's the derivative.
This is movement.
It includes translational and rotational. Does that make sense? Any questions?
So, Mr. Beginner, what you said yesterday, two-body problems?
Right. So now, when you apply, we'll wrap up the lecture with two-body problem statement. Okay? We need to introduce something called relative motion. Okay? Because everything is relative in space. What we'll do is so you have a particle P. Okay. Let's say this is a moving frame. This is the inertial frame. And this is R. And this is let's call this O, and let's call this R. And this is R. So here, R is equal to R naught plus R plus. So think about this as an orbiting body, particle P. This could be your moving frame or Earth. This could be that imaginary inertial frame. Okay. So what you do is, you're interested in this R relative, but you cannot apply Newton's laws in this frame. So what you do is you define, does this make sense? Vector addition. you have R naught plus R relative is R. Got it? It's vector addition. You take this is the first vector and this is the second vector. You join the tail of the first vector and the head of the second vector to get the addition. Right? Now if you take the derivative with respect to time, you're going to get d over dt of R naught plus d over dt of R. Okay? And then you need to apply this to both of these vectors. This or that. So here you are going to get, this will be R naught circle dot plus omega crossed with R plus R relative circle dot plus omega crossed with R relative. Did we apply that? Did we apply this? This is, and introduce another step here.
Is that D prime R over dt? That D prime R over dt? What you just heard?
This is dr by dt is equal to d r dot r o dt plus d over dt r. Okay, this can be written as r naught plus r relative. And I am applying this here and this here. Got it? This would be 0. It's not. So if you look at R naught, this is that vector. Okay. This vector is in this frame. So this frame is not moving. This will be 0. You should know what is moving, and that is what I mean by being able to apply it. So did we use all of this? We did not use all of this. We just used this. We just used this formula for every vector. Okay? Spend some time on this. There is a section 1.6 and section 1.7. Okay?
The older version of the book is fine too, though, right? The older version of the book is fine too, right?
Older version should be okay, but when the problems are assigned, you need to refer the newer version.
When you
Alright guys, I think we need to wrap up.
Sorry, I have
Sure.
Yeah.